Good morning.
Good morning. Good. Amen.
Please write your enrollment number in the chat box. Uday Kiran, please write
Yes,
your
sir, yes,
enrollment
sir.
number in the chat box.
Okay.
All you write your enrollment number in the chat box fast before the commencement of the class. All you write enrollment. Hello.
Yes, sir, yes, sir.
All you write your enrollment number in the chat box so that your attendance can be recorded.
Sorry, no.
Only 3 have written. Please you all write your enrollment number in the chat box so that your attendance can be recorded. Please write. Do write.
Which one?
4 have written. All are requested to write your enrollment number in chat box. Do write fast. After that, your class will be commence. Only 5 students have written.
Okay, on. Okay. Good morning to everybody. Before entering to class, I am instructing you, please write your enrollment number so that it will be recorded. Okay, thank you very much. The first class I have already discussed about the web And that three type of wave, matter wave, electromagnetic wave, mechanical wave. And in your course, mechanical wave and electromagnetic wave, in electromagnetic wave and mechanical wave, there is example. Also, I have discussed about the propagation of sound. And electromagnetic wave, light is the electromagnetic wave. And we have also discussed the important properties of electromagnetic wave are polarization, interference, diffraction. These three are the most important properties of electromagnetic induction. In the last class, we have already discussed about the polarization of electromagnetic wave. We have taken the example of light and how light get polarized. I have already told you. And the today we'll go for another important property of your electromagnetic wave. That property is called interference. In your course, please follow the course of study. The according to your course of study, the interference. What is that interference? Interference, okay. Interference, that is the whenever two light waves, we are discussing about electromagnetic wave. Electromagnetic wave. So light is a electromagnetic wave. Whenever two rays of light having same amplitude and constant phase difference or in phase with each other, both the rays have same amplitude and in phase with each other. In other words, we can say having constant phase difference condition. If two waves, rays of light having same amplitude and same amplitude and constant phase difference or in phase with each other propagate through a medium simultaneously, what will happen? Then the intensity of light gets modified. Modified means you will observe bright, dark swings over the screen. That means you cannot get moderate intensity, but you get either you get dark point or you will get the bright point. That means whenever two rays of light having same or nearly same amplitude and in phase with each other or having constant phase difference, then you will see that the intensity gets modified. Okay, that means bright and dark things are often over the screen. So if you calculate the intensity, if you the amplitude, suppose the amplitude of nearly equal, the amplitude of one ray A1 another A2, and therefore the resultant amplitude square, this can be derived in your book. It has been already derived. Just I want to glance it. A square is equal to A1 square plus A2 square plus 2 into root over A1 A2 cos of delta, where delta is the phase difference or constant phase difference between two waves. Therefore, in place of A square, I can write intensity directly proportional amplitude square. Therefore, I can write I is equal to intensity is I1 plus I2 plus 2 into I1 I2 cos of delta. So this is your delta is equal to how much? That is 2 pi by lambda into pi. This is your intensity, resultant intensity. You see, the phase is equal to, phase is equal to how much? 2 by, we know it. Phase is equal to, it is the definition, 2 pi by lambda into path difference. So you see here the point at which bright point, the position at which bright point is often called constructive interference, and the point that is maximum intense point, and when the point dark point, that is called destructive interference. Let's come to the coherent sources. Coherent sources, two sources of light are said to be coherent if they emit light having same phase difference or in phase with each other. If you take two sources of light, I have already told you two rays of light, so two rays should come to two sources, and these two sources are said to be coherent if they have the light having constant phase difference or in phase with each other, then this is called coherent sources. So the basic condition, essential condition for getting interference patterns, that the sources must be coherent sources. So now next, I will go for under which condition you will get the maxima and minima. You see, for bright point or constructive interference, the intensity must be this intensity must be maximum. Under which condition it is maximum? If cos delta is equal to 1. So that when cos delta is equal to 1, the cos delta means 1 means cos delta is equal to 1. That means delta is equal to 0 degree. But in place of delta, I can add pi by lambda path difference, which is equal to 0. Therefore, that implies path difference is equal to n lambda. You see, 0 means n pi by 2. N pi by 2, pi cancel, therefore n pi. If the path difference is equal to integral multiple of wavelength, then you will get the constructive interference or bright fringe. Similarly, for destructive position, the cos delta is equal to 0. Cos delta means that is delta is equal to 2n plus 1 pi by 2. 2n is the odd multiple of pi by 2. This is equal to 2 pi by lambda into path difference. Path difference is equal to 2 pi cancel. You get 2n plus 1 by lambda by 2. So if the path difference between two interfering rays is equal to odd multiple of lambda by 2, then you will get the destructive interference or diffraction. And if the path difference is equal to integer multiple of path difference, or you can say even multiple of lambda by 2, that can be written as even multiple of lambda by 2, then you will get the constructive interference. So this is your, what is interference? How can you get the interference? Now the interference occurs in two ways. The interference of light occurs in two ways. One is by division of wavefront, another one is by division of in your course, division of amplitude. So interference by division of wavefront and interference division of amplitude. First of all, we go for interference by division of wavefront. See your course of study, you'll see that the interference by division of wavefront. Wavefront, you know, the locus of point having same phase. You see, this is a point source of light. Now these are the wavefront and this is the wavefront. Wavefront, if you take another two slits S1 and S2, which are symmetric with respect to S1 original source, then you see this is the primary wavefront. If you take this point and this point, these are the 2 points, 2 sections of same wavefront. Now the light from this and light from these two sections, this point section, this is light and this is also light. You see the light from the different sections of wavefront, primary wavefront, have same phase, because you know this way, what is wavefront? The light having same phase after same instant is called wavefront, primary wavefront. You see this point, if light goes to this point, this has the same phase as that of this. Light is going from this section and also this section. So these two light have the same phase or in phase with each other. Therefore, these are the two sources of light, and these two, I have already told you, two sources are said to be coherent if they do send the light in phase with each other. Therefore, these are the initial or essential condition for getting interference. Therefore, light from S1 and S2 interfere with each other. If you place a screen near it, then the interference patterns are observed over the screen. This is the experiment performed by scientist Young, so-called Young double slit experiment. Okay, so the interference by division of amplitude, this is one of the most preferable example or suitable example of Young's double slit experiment. So You see Young double slit experiment. Young allowed sunlight to pass through a pinhole S0 and then through two pinhole S1 and S2, which are symmetric with respect to S1. Then the light from a same wavefront from S1 and S2 propagate along same direction in phase with same phase, therefore interfere with each other, and the interference patterns are observed over the screen. Okay, and what is the nature of fring? The nature of fring on the section on the screen is depend on the position of slit with respect to the orientation of screen. Okay, if the screen is here like this, now the analytical treatment, you see this is S0 is here and S1 and S2 are these two slits here. What will happen? The ray from S1 and ray from S2 will propagate along same direction and you will get the interference patterns over the screen. Let P naught is the central point of screen. So central point with respect to slit S1 and S2. Let us take any point P at a distance P naught as a point of observation. Therefore, rays from S1, that is S1P, and rays from S2, S2P will interfere each other and produce the interference patterns at P. Now, I have already told you the nature of interference patterns depend on the path difference between these two rays. So here you see the path covered S1P and the path covered S2P. Therefore, path difference is equal to S2P minus S1P. That is equal to AS2. And it can be calculated that from the calculated, you can calculate this, or if this is a right angle triangle and this is distance of screen from the slit, d square plus this is this is equal to y. This is this is small distance. So small d, this is d by 2, y minus d by 2. So you see, putting all these values, we will get the path difference is equal to how much path difference, yd by d. Yd by d becomes the path difference. Path difference. So you will calculate it, but simply you know the rays from S1, the path difference between the rays from S1 and S2 is equal to yd by d, where y is the position of P and d the distance of separation between two young slits and d the distance of screen from this slit. Therefore, P will be bright. P will be bright if the path difference yd by d is equal to n lambda. Therefore, the position of bright point is equal to nd lambda by d. And P will be dark if yd by is equal to 2n plus lambda. This is the condition we have already discussed in first. So therefore, this is why position of dark point is this small. Now, if you compare, this is when n is equal to 0, then you get the position P naught is bright. N is equal to 1, 2, 3, 4, and etc. Therefore, we'll get the alternate frings, or the we get the dark bright frings alternative order with the central bright fring. This is all about your Young double slit experiment, in which the interference pattern obtained due to the division of wave front. Now the fring width, the distance, this is the fring, this is bright, cross is dark, bright, dark, this is bright. So distance between two consecutive same fring, either too dark or either too bright, this is called fring width. Therefore, the fring width can be calculated as lambda d by d. This is the fring width. So it is observed that bright dark frings are obtained in alternating order with central bright fring. And you see, when the D is very close to each other, the slits are very close to each other, then B, small d will be more smaller, therefore beta will be increased. Therefore, for clear interference, the slits should be very close to each other and screen will be sufficiently distance from the slits. Now, this is all about the fring. Next, what will happen if you take white light fring? In your course, that is white light frings. White light fring, White light, consists of 7 color light, and the 7 color have 7 wavelengths. You know it very well. The 7 sunlight, it has 7 color light, and each light have certain wavelengths. Therefore, when white light is used for illumination of slits, what will happen? Then each monochromatic chromatic pair of light, suppose red light and red light, will interfere, and blue light, violet light. But you will see that for the central bright, then each pair, monochromatic pair of light, produces their own patterns. Like um, red light will produce red color patch, red color pink, blue light color produce blue light pink, violet, and so that. But they are the central, what will happen? You will central depend, does not central, it is zero. Therefore, central does not depend on wavelength. Therefore, the central point will be white. Otherwise, the other light are colored. So at the central position P naught, the screen, the central becomes white, while a few colored things are often on the both sides of the central ping. So as we move either side of the central ping, the first dark point violet, green, blue, yellow, absolute. Now, so whenever white light interfere with each other, then the each pair of monochromatic pair of light produces their own pring, but the at the central, since does not depend on wavelength, therefore central pring will be bright pring, a white pring, while the other color prings are appeared on both sides of the central white prings. And the order of pring as per the big guy, or that is violet, indigo, etc. The Odia that is in Bhagonista Halala, green, blue, yellow, red, etc. Okay, this is all about a white cloud ping. Next course of study, follow your course of study, displacement of ping. So you see this is two slits, this is one slit, two slits, and these two rays, this is then S1P and S2P interfere each other, produces patterns at P. If you keep a thin transparent glass or transparent medium on the path of either rays. Suppose I have put a piece of mica or glass of thickness multi on the path of first ray S1P. What will happen? Then the path difference gets changed. When the path difference changes, I have already told you the nature of interference patterns depend on the path difference. If nature of pattern depends path difference, you see by introducing a transparent media, that may be glass, may be mica, whatever may be, on the path of either interfering rays or one of the interfering rays, then you will introduce, or we will provide extra path difference, for which the pring shifts. When the pring shifts, and if the displacement of pring, what is the shift of pring, how much distance is shifted, if P is here, suppose the nth bright point is formed here, then that nth bright point will shift it to other position, and that shifting position is equal to y naught, which is equal to d by d mu naught 1 by t. You see the shifting position depend on the thickness and refractive index of the medium, which is kept on the path of the one of the interfering rays. So the shifting depend, this is the displacement of pings. How can displace the pings? The ping can be displaced by introducing a transparent media like glass or mica on the path of either ping. Therefore, what will happen? You will see the ping will be shifted to a distance d by d mu naught. The ping displacement depend on the refractive medium and the thickness of the media. Okay. Now the second type of your okay. Now let's come to your another interference by division of wavefront. I have already told you the interference due to division of wavefront is by the young double slit. Also, another arrangement is there, that is Lloyd's mirror and Fresnel biprigine. You can get also the interference patterns by division of wavefront by using Lloyd mirror and your Fresnel biprigine. What is that Lloyd mirror? Lloyd mirror, it is simply a plane mirror. Lloyd mirror, it is simply a plane mirror. Plane mirror, what you are using in your day-to-day life. This is a plane mirror. Here, this is a plane mirror. This is plane mirror. If you put a source of light at S1, what will happen? The ray of light, one ray of light, this is the ray, get reflected along this point and move to A. And another ray at the two extreme position of mirror, another ray S1, M2, and this will reflected along these two rays. Therefore, when we produce it, then they are diverging nature. But here you see they appear to come from another point S2. Therefore, S2 will be the virtual image of S1. Virtual image of S1. Now you see all the rays in between AB, because you have considered these two rays on the two extreme positions of the mirror. If you consider and all other rays in between the two extreme positions lie in between AB, you will see that all the rays which all the rays appear come from S1 and S2. Actually, the ray which is coming from S1, they are divided into two parts, that is which is appear to come from S1. Rays, the direct ray from S1, and the rays, the after reflection on the mirror, that is appear to come S2, have the constant phase difference pi. Why? You know, the whenever light get reflected on a denser medium surface, extra path difference lambda by 2 or phase difference pi is introduced. So you see all the direct ray from S1 and the reflected rays from the mirror, that is appear to come from S2, have the constant phase difference pi. So this is the essential condition for getting interference pattern. That means all the rays in between, all the rays directly coming from S1 and appear to come from S2 have the constant phase difference. Therefore, S1 and S2 are the coherent sources, which is the essential condition for getting interference pattern. Therefore, they will interfere with each other and produce the interference pattern on the region A and B. Okay, A, B, A and B. So this is the interference pattern, and the expression I can write. This is if you place the S1 at a height d by 2, then the image will form at d by 2. Therefore, total distance d1 here and d is here. Then the fringe width you can observe over the screen. This is the screen. What is the fringe width? Fringe width lambda is equal to how much? Lambda d by d. Capital D, lambda capital D by d. Beta is equal to. Beta can be measured from the screen, and applying the value of small d and a capital D, lambda can be determined. So applying plane mirror, you can measure the refractive index from medium. And in the previous experiment, Young's modulus, Young's double slit experiment, you can measure the refractive index of media and as well as the thickness of this media by putting this formula. Because measuring D naught can, Y naught can be measured, D can be measured, D can be measured. Therefore, if T is given, then mu can be determined. If T is not given but mu is given, you can. So let's come to another experimental arrangement for getting interference patterns by division of wavefront. That is your Fresnel biprigine. The another is Fresnel biprigine. Uh, 1 minute, wait 1 minute, 1 minute. Okay, again come to our topic. So the let us take another experimental setup for getting interference by division of wavefront. That is your Fresnel biprism. Fresnel biprism. It is Fresnel is a name of scientist, and biprism he made a prism by taking two identical right angle prism joined at the base. You see, this is one right angle prism. This is another right angle prism. They are joined at the base. What will happen? You get or we get this is the Fresnel biprism. Okay. Now, when a source S is kept in front of a Fresnel biprism, what will happen? Then you see upper part of the biprism. This is one ray, this is another ray. Then the ray is after refraction moves along this direction, and it appear to come from some other one. And another ray on the another extreme position, this is the ray and moves along this direction. Therefore, both the ray, this ray and this ray appear to come from S1. Therefore, S1 is the image, virtual image of S due to the refraction through upper part of the biprism. Similarly, in the lower part of biprism, this is one extreme ray moves along this direction. Another ray at the extreme position, this move along this direction. So both the ray appear to come from S2. Therefore, S1 and S2 are the two virtual images of S. Virtual images of S. So you see within the region AB, all the rays in between AB appear to come from S1 and S2. You see, this ray may lie this. So similarly, this ray lie this. So this AB, the region at which two rays uh, produces the interference patterns. That is, rays which are actually coming from S appear to come from S1 and S2. So the set of rays which are really coming from S appear to come from S1 and S2 have the same phase and same amplitude. So they produces the interference patterns within the region AB of this screen. Okay, now you see here S1 and S2 are the two coherent sources because both have same weight, both have same phase or in phase with each other. Therefore, they are the coherent sources so which are the essential condition for getting interference pattern. So you get the interference patterns here. Now this is the distance, capital small d this and capital D the distance is source and the screen. Now the you see actually coming from app interface the production so here the central is bright fringe, but in the case of large mirror, the center you will get the dark fringe because extra part difference is added here. Now the interference due to also by biprism you can determine the wavelength of light used by the formula. The thing with measured thing produced over the screen can be measured and d can be small d can be measured and d can be measured. So lambda wavelength of the light used can be measured by using Fresnel biprism. Next, the interference due to division of amplitude. Interference, I have already told you, interference can be occurred due to division of wavefront. Division of wavefront means the light from different section of same wavefront. But here, the interference can be obtained by division of amplitude. Division of amplitude, you see, division of amplitude. So, first of all, interference division amplitude. In this topic, we'll discuss how the interference fields are obtained by two interfering rays derived from a single incident beam by division of amplitude. A single incident beam here, and you will get by division of amplitude, it get divided in two parts. So you see what happens whenever light incident on the semi-transparent surface. When light incident on the semi-transparent surface, or this is a medium, this is another medium. Suppose this is rarer medium, it is denser medium. So when light incident on this point, a component reflected along this direction and transmitted along this direction. So you see here, with the same ray, we get the reflected component and transmitted component by division of amplitude. So my point here, the phase change on reflection. When light wave is reflected from boundary of an boundary, there is an abrupt change in phase. When light is reflected from a boundary, or light reflected from the boundary of a denser surface. That means when light is going from rarer medium to denser medium, suppose light is going from rarer to denser medium. So what will happen? You will see when it get reflected on the surface of denser medium, there will be sudden change in phase. Phase change, phase becomes opposite. That phase becomes a pi. So phase changes. How much phase changes? Phase changes the value pi. Phase changes. So when light going in the rarer medium and get reflected on the surface of denser medium, there is abrupt change in phase. That means phase change is pi. Pi phase change is equivalent to path difference lambda by 2. I have already told it. Phase change pi means path change lambda by 2. So there is, but whenever light traveling in the denser medium and reflected on the surface of rarer medium, there is no change in phase. Only phase of light changes when it gets reflected on the surface of a denser medium. Now Stokes analysis, Stokes has analyzed this and he proved that there is change in phase is pi. So according to Stokes analysis, in order to investigate the phase change in reflection light at the interface between two media, Stokes used the principle of reversibility. The principle of reversibility, it said that a ray of light may be reflected or refracted, or will the retrace its original path if the direction is reversed, provided there is no absorption of light. That means light incident along this direction and this moves along this direction. If the direction, this is the incident ray, again this is the transmitted ray and this is reflected ray. That means light will, suppose the original light is moving from this along this direction. It incident and it divided two parts. One is reflected, other is transmitted. Similarly, if this becomes incident ray, this becomes transmitted ray, and this becomes your reflected ray. So my point is, if the according to Stokes, that ray of light may be reflected or refracted will trace the original path if the direction is reversed. This is provided there is no absorption of light. This is your Stokes analysis, and in your course there is Stokes analysis and phase change due to next phase change Stokes analysis. Now interference film. Now I have discussed how the interference patterns are obtained due to division of amplitude, and a more suitable example of interference due to division of amplitude is the thin film. Interference is thin film. You see, this is a thin film. You see, this is the thin film. Okay, having refractive index, suppose mu, and the your thickness is T. Now, let us take a incident ray. This is the incident ray. Now, at this point, a part is reflected along R1 and a part is refracted along this, and it incident on the other face, and then it is transmitted along T1. Similarly, at this position, it is reflected part moves along this direction and incident on the upper surface of the film and get reflected along like this. And say at this position, and the refracted part like this, reflected part like this, and moves transmitted along this direction. So you see, by a single incident ray, you use a single incident ray, but you will get how many? A set of reflected rays on the upper side and a set of transmitted rays on the other side. So here, a reflected ray set produced along upper side, while a refracted ray, or you can say transmitted ray, along the other side. But in each of the set, the amplitude decreases rapidly. Here, the amplitude of machine is something A1. A, it becomes A1, A2, A3, A. Similarly, A1 prime, A1, 2 prime, A3 prime, etc. So the amplitude of the set of rays decreases rapidly from one ray to next ray. Therefore, a set of rays as originated from same source have produced with the division of amplitudes, and they enter the set of reflected rays interfere with each other, and also set of refracted rays interfere with each other. So you see, if you keep put screen here, you get the interference pattern due to reflected component, and in this side, lower side, you'll get the interference pattern due to the interference of transmitted rays. So my point is, what is the nature of fringe? Let us consider the reflected component. The part difference between the reflected rays, this is a reflected ray, this is another reflected ray. So you see here, this is reflected and this is reflected ray, but these are the two interfering rays. Now the part difference, if you will not introduce the, here it is moving like this, but it passes through a denser medium. Therefore, the extra part difference is lambda by 2. And if you calculate this, the part difference between ray R1 and R2 is equal to 2 mu t cos theta plus lambda by 2. Lambda by 2 extra part difference due to the reflection on the upper surface of the upper surface. But it is originally, screen is here. From this position you have considered. But this is coming to this, then it moves like this. So it passes through the denser medium. Therefore, extra part difference lambda by 2 is introduced, and the net part difference we can calculate it, or it is calculated in your textbook, that is 2 mu t cos theta lambda by 2. Part difference will determine. Now you can find what are the natures. So if T is the thickness of film, mu the refractive index of film, for maxima 2 mu t cos theta is equal to n lambda, because part difference is equal to n lambda, and for minima 2 mu t cos theta by theta plus lambda by 2, 2n plus lambda by 2. Therefore, you can measure the width of the fringe lambda d by d. Okay, now putting the values we can find the mu can be determined, the refractive index of the thin film can be determined, thickness also can be determined by using this formula. Okay, now we get the interference due to division of amplitude by taking the example of thin film. Okay, now let's come to fringe of equal inclination. In your course, there is interference due to thin film, qualitative description of fringe of equal inclination. What do you mean by equal inclination? Equal inclination. Light from a extended source will reach the lens from various directions, and the fringe patterns will be spread over the large area of the film, and the fringes appearing various points called fringes of equal inclination, and the equal inclination of fringes that are seen this manner for thickness for thick plate are known as hinders fringes. Okay, so you see, if you consider the extended source here, then the fringes obtained, and by lengths you can you see here, from a extended source, if you will take extended source, then you will get number of springs in various direction, and that spring spreads all over the large area of the film. And these springs obtained at the larger area are called, at various point on the larger area, are called springs of equal inclination. Okay, if you take a extended source, then the interference springs are often, or pattern will be spread over large area, and the springs appearing various points on the larger area are called springs of equal inclination. So the springs of equal inclination can also seen if you use the thick plate. Here we have considered the thin plate. In this example, you have considered the thin plate. This is the thin, but thick plate. Taking the thick plate, you can observe the fringes of equal inclination, and in this case, known as Heidinger's fringe. Okay. In the next, in your course, that is your follow the course of study, qualitative fringe inclination, finger fringe. Fringes of equal thickness. Fringes of equal thickness, the interference fringe which dependent on the thickness T rather than R is referred as fringes of equal inclination. So you see here angle of refraction, if the fringe depend on T only, the thick, then the interfering fringe will depend on the thickness of T, that is the T, the dominant character, then rather than referred as the fringes of equal thickness. Okay, this is fringes of equal thickness is over. Next, come to interference of wave shape film. The interference due to division of amplitude, uh, again can be another example, or we can cite another example, that is interference by wedge shape film. Wedge shape film, if the film is rectangular, in the case we have considered the film is rectangular. If this is not rectangular, suppose this is one plane, another plane is inclined with this. These are two parallel planes. The medium is bounded by two parallel planes. If this is one plane, another inclined with this plane, that is then the wedge shape film can be obtained. You see, this is one plane, horizontal direction, this is another plane, making an angle theta with the initial plane. And this is the in-between medium is the wedge shape film. Okay, so what is wedge shape film? The film of varying thickness. The thickness is not same here. The thickness is 0 here, and increases maximum. The varying thickness, that is not plane parallels, but parallel planes, but wedge shaped spread film. And it consists of two non-parallel plane surface. In case of interfering, they do not enter the eye parallel to each other, but appear to diverge. So here you see, this is one ray, then reflected along this direction. The another component which is refracted gets reflected at this surface, so that in the two rays here. So you see, this ray is reflected on the surface of denser medium, and this is on the surface of rarer medium. Therefore, the extra part difference is introduced. Here, the constant part difference is introduced. Therefore, these two rays, 1 and 2, are actually coming from or originated from this ray. That means this ray is splitted off into one ray and two ray. One is reflected component, another is transmitted component. The reflected on the surface of medium, thick, denser medium, and another is reflected from the surface of rarer medium. Therefore, they will interfere with each other and produces the interference patterns over the skin. But here, in the case of that two parallel planes of thick film, the ray enters parallel to each other to the eye. But these two rays are diverging nature. They do not enter parallel to each other to the eye. Therefore, do not enter the eye parallel to each other, but appear to divert from point near the film. So here the additional part difference I have already introduced. Here the part difference between the two ray 1 and 2 can be calculated 2 mu t plus lambda by 2. 2 mu t plus lambda by 2. Therefore, the condition for brightness is equal to plus or minus, that may be plus added plus this is equal to this or mu to this small. Similarly, dark condition is like this. So here, if you the fringe expression for fringe width, if you derive the expression for fringe width, then beta fringe width is equal to lambda 2 mu theta. Lambda 2 mu theta. Now 2 mu n. So now you can find the mu. Mu can be determined, also lambda can be determined by beta can be measured, theta can be measured. If lambda is given, then mu can be determined. If lambda is given, mu can be determined. So this is another examples of the interference getting by division of amplitude. That is your first thin film, second wave-shape film. Next, the Newton ring. It is also the interference patterns over the screen due to the division of amplitudes, and that is example of, this is also examples of the wave-shape film. Wave-shape Newton device instrument. It is the most important application of interference due to wave-shape film, or that is wave-shape film, which is an example of division of amplitude. So here the Newton ring, the apparatus consists of a piano convex lens. This is plane surface, this is convex surface, and a glass plate. This is a glass plate, this is a piano convex lens. Now the piano convex lens is placed over the glass plate with the convex side on the glass, touching the glass. You see this section, this is a wave-shape film, this is the wave-shape film. So the medium whose refractive index is to be determined, they will kept within this wave-shape film. Now the interference, likewise, the light incident this, and it is divided into two parts due to the division of amplitude. First part reflected over like this, and second part is transmitted like this. So these two rays interfere with each other, and you will get the interference patterns placed over the screen here. Placed over the screen here. Now, what will happen? Now the reflected components interfere with each other, produce the interference rings. So therefore, the rings are concentric and circular. The rings which are often over the screen are concentric circular, and with the dark ring at this place. Why dark? Because here also the part difference, extra part difference lambda by 2, because this ray reflected from the surface of the denser medium, but this is from rarer medium, and you get the interference ring circular in nature. Now it is observed that the diameter of bright ring is proportional to square root of odd natural numbers. If you take the bright ring, suppose this white is the bright ring, the bright ring diameter is proportional to it is observed, or it can be calculated that the diameter is proportional to the square root of odd number, and the diameter of the dark ring square root of the natural number. And from this concept we can find the expression for lambda is equal to dnpn square. So this lambda can be determined by using the Newton's ring. So Newton's ring is an example of wave-shape film, and also it is the interference pattern obtained by division of amplitudes. Now the another most important and experiment which comes to your exam, that is Michelson-Morley experiment. Michelson interferometer. Michelson is a name of scientist, and the name of a scientist Michelson Michelson interferometer, it is he derived a device, an excellent device to get interference rings by various shapes and by changing the path difference at will and due to changing of position of mirror. So in the Michelson interferometer is an excellent device to get interference ring of various three things. In case of Newton ring, you get circular ring. But Michelson interferometer, you can get circular ring, you can get straight ring, you can get curved ring. Therefore, according to our will, according to our desire, we can produce the interference rings by changing, and also we can provide the required path difference. The experimental setup is shown in the figure. The experimental setup consists of a point source of light, two identical glass plate G1 and G2, and two plane mirror M1 and M2. Here M1 is fixed, while M2 can be moved and also can be inclined. There M1 and M2 are two inclined position or normal position. There can be then G1, G2 are the two plates, like identical glass plate. What will happen? You see, this is a point source of light, and light comes to this position, and here it gets refracted along this, and this is a semi-transparent glass plate G1, and at this position P, it can be divided in two parts, or it is division amplitude two part. One is refracted or transmitted along this direction and incident M1. Another is reflected along this direction. So you see, from the semi-transparent surface, they get divided two parts. One is reflected along 2, and another is refracted along 1. So these two rays, since M1 and M2, these two glass plate, this glass plate is makes an angle 45 degree with the 45 degree with the horizontal. So in order to have rays incident normally, so it is kept in 45 angle. Therefore, this ray incident normally and come back along this direction and for reaches at this point. Similarly, this ray incident normally and back again at this position. And you see here, both the rays moves along this direction. But the problem is here. What is that problem? The ray 2, which is reflected back from M1 passes through the glass medium twice.